addition, tomorrow we'll also look at network flows. Connectedness is an important idea in graph theory. Essentially what we are looking for is a graph which is not just connected, but is highly connected. What does that mean? For a connected graph, you can go from one vertex to the other on a path. But something like if you have a tree, for example, and if I remove any one vertex from that tree, not a leaf, but a non-leaf vertex, then you don't have a path from every vertex to every other vertex, because that path will get broken. Therefore, tree is connected, but is sort of not highly connected. We won't call a tree highly connected. Whereas in case of cycle, if you remove one vertex, any one vertex, then the remaining graph that you have still remains connected. It still remains connected. Such a thing we would want to call two connected. So you'll have to chop off at least two vertices to disconnect a cycle. So higher levels of connectivity are desired. In general, the rule would be more edges you have, more is connectivity. Something like complete graph is highly connected. Complete graph is too highly connected. But on the other hand, complete graph has too many edges. Complete graph has too many edges. So this is kind of optimization situation that have been haunted with this idea. In all the studies of graph theory, we would want to have fewer number of edges, but at the same time, we want to have connectivity as large as possible. Okay, so let's begin with a definition. Connectivity of G is disconnected or has only one vertex. Is K connected if okay, so let's view connectivities of few graphs. What about connectivity of 7? So I have a cycle with 7 vertices. If I remove any one vertex from a cycle with 7 vertices, then the resulting graph, is it clear what I'm saying? If I remove any one vertex here, the resulting thing will be a path. The resulting subgraph will be a path. Is that clear? If I remove the vertex 4, Therefore, you need to remove at least 2 vertices to disconnect this graph. So the smallest size of course you can remove, you should not be removing 3 and 4. That's not a vertex cut. 3, 4 does not form a vertex cut because the remaining portion is still connected. So you have to choose your vertices properly. Something like 3 and 6, they form a vertex cut, or 1 and 5, 2 and 4. Any one of these forms a vertex cut. So minimum size of a vertex cut is 2. Therefore, the connectivity of C7 is 2, or for that matter connectivity of any cycle is 2. Any cycle has connectivity 2. Connectivity of a tree is 1. Connectivity of path is 1. Put in this way, what this is saying is the cycle has k of g equal to 3, k of g equal to 2. Cycle is 2 connected, it's also 1 connected. Is that clear? It is also 1 connected because that is the way. It's also 0 connected. Alright, so it's hierarchical, so we have to keep that in mind. For example, if your graph is disconnected itself to start with, then I can take S to be empty set. I can take S to be empty set and then the connectivity of a disconnected graph is 0. Connectivity of disconnected graph is 0. Graph that has more than one component, then the connectivity is 0. That is to be intuitively expected. So that's sort of a right line. What about something like connectivity of complete graph? So you have m vertices on one side, n on the other side, kmn. How many vertices would you have to remove to disconnect this graph? All the vertices in one part. You'll have to remove all the vertices. So the connectivity is minimum of M and N. It's a minimum, smaller of the two. If you can argue. If you have some vertices left here and some vertices left here, then the resulting thing is still connected. That's clear. It's very clear. So you have to remove all the vertices in one part or all the vertices in the other part. So in fact, the vertex cuts must include either this part or that part. And because we need smallest, it's the minimum of the two numbers. What about the connectivity of the cube graph? Okay, so let's look at Q2 first. Q2 as such is equal to C4. Q2, this is Q2. Connectivity of Q2, just saw that there, is 2. So we expect that connectivity of Q3 should be equal to 3. Okay? How do we see that? So you just have to argue that a vertex cut in Q3 cannot have size 2. If you just remove 2 vertices, then you cannot remove 2 vertices here and 2 vertices here. You certainly cannot do that. So in one part you will not be removing 2 vertices, but will be removing either no vertex or remove 0 vertices. Then that will remain connected, the remaining portion, because k of Q2 is equal to 2. So that part, suppose I remove this vertex, the remaining portion still remains connected. Now I can use these edges in the matching from, so there is a copy of Q2, there are 2 copies of Q2 from which Q3 is constructed. So in one part things remain connected. In the other part also, if things remain connected, then you are quite all right. But how is that clear? Because you could not have removed all the both of these. Just so let's prove this theorem. Proof. Induction on K. When K is equal to 2, Q2 is C4. So let K be at least 3. Qk is constructed from two copies. Say so there is a Qk minus 1, 1. Suppose we have a vertex cut S with at most K minus 1. Then vertex set of it cannot pick up K minus 1 vertices from here and also K minus 1 vertices from here, because the total then by induction Qk minus 1 is connected. Because you are removing only K minus 2 vertices and not K minus 1 vertices. In order to disconnect this, you need at least k minus 1 vertices by induction hypothesis. For each vertex, in qk minus 1 second copy, we look at the corresponding vertex. Go up that way. How many of these are there anyway? How many of these are there? Not far too many. This has as many as 2 raised to k minus 1 vertices, out of which you would have dropped only k minus 1, not more than that. Okay? At least one vertex in qk minus second copy is adjacent to a vertex which has not been deleted. And the corresponding thing here is connected, therefore you are through. That's all. Okay, so I'll complete this argument. All right. Yeah, in fact, work with this first and then write an argument in general. What about the connectivity of complete graph? Complete graph has no vertex cut. Complete graph cannot really have a vertex cut, that's clear, because no matter how many vertices I remove, the resulting things will still be connected. Is that clear? Now I have to use the second part of the definition. OR has only one vertex. Okay? So the connectivity of Kn is n minus 1 by definition. Okay? In fact, complete graph is the only graph, think about it, that has no vertex cut. That has no vertex cut. Any graph which is not complete will have a vertex cut. It will have a vertex cut. You can certainly remove some portion so as to disconnect that graph. That's because not everything is an edge. Okay. So if you look at the, incidentally the one part is, we didn't look at is connectivity is no bigger than the minimum degree. That is clear. I can always disconnect a graph using proof, take a vertex, except when is that clear? See, what we are saying is this is a vertex, so if I remove this portion, that vertex will be separated from the remaining things. This argument will not work only in case all the vertices other than x are adjacent to x. Then because then nothing will be left here on the third level. Is that clear? Nothing will be left. And then it is not a vertex cut. It's really not a vertex cut. But that happens only when you have complete graph. So when you have a non-complete graph, equivalently what I am saying is if your graph is not complete, delta of g will not be equal to n minus 1. Delta of g will be less than n minus 1 because not every two vertices are adjacent. So delta of g, the minimum degree, will be less than, therefore I can find a vertex which is not adjacent to all the vertices. Just pick up that vertex. So there will be something at this level. Okay. So you will be separating that x from those vertices. So this is a vertex cut. The argument is trivial in case your graph is complete. If your graph is complete, then delta of g is n minus 1, and then we have already seen that here. So that is okay. What that means is, if you add up so if you add up all the degrees, which is equal to 2 times the number of edges. So E of g is greater than or equal to k times n divided by 2, where k is equal to connectivity. Number of edges is at least. This bound is sharp in case, so consider qk. What is the number of edges in qk? Qk is k regular. Qk actually is k regular. N is equal to 2 power k. So what I am saying is, in case of the cube graph, this bound is sharp. You have exactly as many edges, minimum number of edges. So cube graph is good in this sense. If you want to have a graph whose connectivity is k and the graph has 2 raised to k vertices, then it must have at least these many edges, and the cube graph has exactly those many edges. Cube graph has exactly these many edges. So if you remove some edges from the cube graph, it will not remain k connected. It will not be k connected because that's what we have proved here. Okay. So in case of cube graphs, you have sort of achieved something that attains this threshold. Unfortunately, the cube graphs have the property that number of vertices is 2 raised to k. Number of vertices is 2 raised to k. What if the number of vertices is not equal to 2 raised to k? Can I construct graphs that have this property? That is the kind of situation I am looking for, is the graphs that are k regular, n vertices, and are k connected. A k regular graph cannot be expected to have connectivity greater than k. Is it clear? This is that connectivity is never greater than the minimum degree. Connectivity of a graph is at most the minimum degree. And this is the idea behind the construction, what is called the Harari graphs. So is constructed as follows. For vertex set of Harari graph is the arranged on a circle. So let's see what he's saying. You need to make cases here. K is even. Then I would make 0 adjacent to 1, 2, 3, 4 up to R. I am going to read everything modulo n. Is that clear? I am going to read things mod n. 0 is adjacent to 1, 2, 3, 4 up to k upon 2, that is R. Also adjacent to minus 1, minus 2, minus 3, minus 1 is same as n minus 1. Plus or minus 1, I plus or minus 2, I plus or minus R. Everything mod n. For example, if I want to have Harari graph zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 adjacent to 1, 0 adjacent to also 2, 0 adjacent to 9, which is same as minus 1 adjacent to 2. Then 1 adjacent to 2, 1 adjacent to 3, 1 adjacent to minus 1. etc. Is that clear? So one can complete this picture. Okay? I won't draw all the edges. 2 adjacent to 0, 2 adjacent to 1, 2 adjacent to 3, 2 adjacent to 4, 3 adjacent to 5, 4 adjacent to 6, 5 adjacent to 7, 6 adjacent to 8, 7 adjacent to 9, 8 adjacent to 0, presumably we're done with. Each vertex here has degree 4. In general, each vertex will have degree k. It will have degree k. It is adjacent to r vertices ahead, r reading things counterclockwise. It's adjacent to r vertices ahead and r vertices behind. Is that clear? So the total degree is 2r equal to k. K regular. Being k regular, the minimum degree is k. Delta G is equal to k. So the connectivity will not be any bigger than k. It can be at most k. We want to say that it's equal to k. Why is that so? Because the argument is as follows. Let S be a vertex cut. We claim that suppose not, what do I have to show? I should then prove by contradiction, so I have to show that G minus S is still connected. Consider and let, without loss of generality, 0 belong to G minus S and some J belong to G minus S. So this is not removed and this also has not been removed. Okay, you removed some vertices. But 0 is retained and J is also retained. Now there are two ways of going from 0 to J. One is that way, other is that way. Is that clear? On one of these two ways, the total number of vertices you have removed is 2r minus 1. So in one of these ways, so this forms two parts. Let's call this part A and that part B. Let AB refer to the two portions of the circle from 0 to J. Then one of these parts A intersection S has to be, because the total is only 2r minus 1. Say, without loss of generality, now I can argue that for every vertex that survives, look at a vertex here in G minus S. How many vertices have we removed from, in A, the number of vertices that have been removed is r minus 1, whereas this vertex totally on this side has r neighbors. It has r neighbors by construction. It has r neighbors. So not all of them could have been removed. At least one neighbor will survive, because you could not have removed all the r neighbors, because the total you have removed is only r minus 1. Therefore, from suppose this vertex survives, then one of its neighbor also survives, then one of that fellow's neighbor also survives, and therefore you can obviously go up to j. That's clear. Okay? So that is the proof that this remains connected. So let's write this down. Each has r neighbors ahead of it, of which only r minus 1 are removed. We get a path in A without S. Thus, a contradiction. Why is this contradiction? Because we said that this is a vertex cut. So every vertex cut has to have size at least k. That is only case 1. In case k is even, the life is quite nice. In case k is odd, I would have to do something different. So let's see what is it that we have to do. So this is so Harari graphs have the property that this bound is exact. This bound is exact. Number of edges is, because each vertex has degree k, it's also k connected, therefore you get equality here in this lemma, etc. So the Harari graphs are good in that sense. What if case 2, k odd, if I cannot really construct a k regular graph on n vertices if n is also odd. Is that clear? The basic degree sum formula, chapter 1. Okay? You cannot have a 3 regular graph on 7 vertices. That is not possible. So if k is odd, n must be even. Now you essentially do the same thing as we did there. Let k be equal to 2r plus 1, n be equal to 2m, as before, as in case 1. I is adjacent to I plus or minus 1, I plus or minus 2, I plus or minus r. That will mean the I is adjacent to r vertices ahead of it and r vertices behind it. And also I plus m. Yeah, that vertex 0 is adjacent to 5. Okay? Diametrically opposite. So those are the only additions. 1 is adjacent to 6, 2 is adjacent to 7. Okay. Diagonally opposite. This also, the connectivity for this is k, will require little more work. It will require little more work, but that is similar. Okay? Just as one talks of connectivity for vertices, one can talk of connectivity with edges. So one can remove edges. As you know, removing edges is a different process. When you remove a vertex, what way is it different? When I remove a vertex, all the edges at that vertex, they go away. Is that clear? Automatically the edges also go away. Whereas when I remove edges, vertices remain. Vertices will remain there. So removing edges and removing vertices are different things. They are quite different phenomena. Definition: disconnecting such that G with F removed is disconnected. K prime G is minimum F that are disconnecting set of edges. So this is the version of connectivity for edges. Okay, that is what we are saying. There is a relationship between the K prime G, let's call this edge connectivity. So just as you have vertex connectivity, this is edge connectivity. Let's get an idea what the relationship between the vertex connectivity and edge connectivity is. Okay, this is a deeper theorem. Theorem. Vertex connectivity is less than or equal to edge connectivity, and edge connectivity is less than or equal to the minimum degree. Proof. What does that mean really? Can I now remove these edges? If I remove these edges, then the graph will become disconnected. Is that clear? X will be remaining word. If we all the edges incident This is a disconnecting set of edges. What is not obvious is inequality. More difficult inequality, that the vertex connectivity is less than or equal to the edge connectivity. It requires some. What is it that we mean by edge connectivity? The least edges whose removal will make the graph disconnected. Mean to say that portion. Consider a set of with smallest f. Then let the two components every edge has one vertex in S and one clear rule. It cannot have both the edges in S. If both the vertices in S, if that was the case, I could have obtained because the okay, the smallestness. From S to S bar, E is in F. Yeah, that is also clear because if not, these will not get separated. This will not get every edge from S to S bar. I'm not saying that this is a bipartite graph or anything like that. But whatever edges there are in the original graph, they all will have to be in F, is what. Let each vertex this is like bipartite graph. That's exactly the situation. S and S bar together form a set of n vertices. So this product, the minimum So the only case I am left with is, now let sum xy are not adjacent, x is not adjacent to y. There is no edge from x to y. What we will do is, we will then show that this edge cut f has at least as many edges, will form a vertex cut, and will show that that vertex cut has size smaller than or equal to that of f. Prime is not equal to x. So there is an edge going from T2 set of all those heads that are in S bar such that so this is just the neighborhood let okay. For every z here, suppose this z1, z2, etc., I get a different edge. Then for every x prime here, not equal to x, I get a different edge. So the number of edges, T is a set of vertices. For each vertex in T, we get a different edge in F, which implies that size of T is less than or equal to size of F. If we can now show that T is a vertex cut, then we are through. That's exactly what we're looking for. We claim that T is a vertex cut Look at what you have done. You have removed the neighborhood of x completely. Neighborhood of x has been removed completely. That is the totally. So from x, if I want to go to y, how is it that I will go from x to y? I cannot jump from to that side. I will have to use some internal thing here, x prime. Okay. But you have also removed all the vertices in S other than x. So these are all removed. Therefore, there is absolutely no way you will be able to go from x to y. Is that clear? You have taken care to see to it that G minus T has no path left from X to Y. All of S without X and neighborhood of X in S bar G minus T has no xy path, which implies that T is a vertex cut. So, K of G, which is the minimum over all such T's, and T itself has size less than that of F, and F has size equal to K prime G. Hence, these bounds here they are not sharp. You can construct graphs. So I will draw a graph and then we'll find out what are K of G, K prime G and delta G for that graph. Is it clear that graph is connected? Find smallest size of a vertex cut, minimum degree and smallest size of an edge cut. See that they will satisfy this inequality, but you really don't have equalities there. So we'll stop here.